Howdy, so this is example 2-4. I'm going to put that right up here, 2-4. And let me pull that in. So I'm going to solve this problem incorrectly the first time just to show you something, and then we're going to solve it correctly the next time because it's going to give us the actual answer. So I think we'll learn more that way, and you'll see why in a minute. So let's just do this. Here, this is a Kirchhoff's current law problem. What we have here, essentially, we're trying to apply KCL, Kirchhoff's current law, to try to find out I1. So what is the current up here? And so the problem gives us this example that the voltage across the 4 ohm resistor is 8 volts. So that's 8 volt drop over there. Then determine I1. So that's the information we're given. So V4 equals 8 volts. I'm actually going to put that down here just to not confuse us because we might need that later. Equals 8 volts. Now, there's a couple of things I want to call out on this that I would not have designed this way. So right now it says I2 and it refers to this as V4. I would have called this I4 and V4 just to keep them the same, but the book didn't do that. So we're going to ignore that part. The second thing that I would have done differently, actually nothing yet, we'll get to that in a minute. So to solve this one, the first part that we're going to have here, I do out equals in. Because remember, the sum of the currents coming in and out of a node equals 0. So essentially, out equals in, or out minus in equals 0, or however you want to do this. So what we're going to do here is we're going to pull some of these currents around to make it a little clearer. Because I'm going to take this point right here, because this is the one closest to V4, which is the one we know. So I'm going to slide this I1 down. So I1, because remember, going through any part of before or after resistor, the current is the same coming in. There's no other nodes coming out, so there's no splitting of the currents. So I can easily just slide this one down. Same with this I2. I can put this I2 over here. I2. See, that's why I didn't want to write in there too much before. So we have I1 coming in, I2 coming out, and then we have a 10 amp coming out. So coming out, I'm going to have what? The two things that I'm going to have, 10 amps out, plus, what is this? I2, and then we have coming into it equals I1. So that's, we don't know what these are yet, but we're going to save it. So the next part we do have is we know the V, the voltage drop at this one, equals 8 volts. So to be able to solve that, V equals IR. Okay, so the voltage at, and we're going to call this V4. So V4 equals, and remember we have I2 here, so equals I2, and then this is the resistor. We're going to call this the 4 ohm resistor, R4. So V4, which we already have, 8 volts, equals I2, which we don't know, times R4. R4 equals 4 ohms. So I2 equals 8 over 4 equals 2 amps. All right, that was how we solved for this, but there's a trick here, and that's how I originally solved. So we're going to put the 2 amps in up here. 2 amps equals I2, so 10 amps plus 2 amps equals I1. I1 equals 12 amps. Cool. The problem is with this one, the reason this is not right, none of this is right at all, is because of this. This is wrong. So if you look carefully in the problem I gave you before, the negative is on this side and the positive is on this side. What does that mean to the circuit? Well, let's look over here. This is a source. If we flow through this in the direction of current, we're going from negative and then positive. So nothing, negative, positive, nothing. So if we go over here, we have nothing, negative, positive, nothing. This actually isn't a resistor that's taking energy out. It's a resistor that's giving energy to the system, which is a little weird. Which means this whole equation going down here is not correct because the outs are not actually coming out. This is actually putting current going the other direction, which is a little weird, but we'll get to it in a second. So because of this, we have out equals in again. Remember to cross this out, just one line through, just so you know that that was wrong, because This is actually what the book gave us. I wrote it improperly. So negative and then positive. So what we have here is, again, at this node, we have 10 amps, and then instead of a positive 2I, we have a minus I2. Because remember, this is going in, it's actually coming out, so we have it over there. Equals the in equals I1. So we can rearrange that. 10 amps equals I1 plus I2. Okay? So both of those are the same equations, just pulled around. So now we're going to do the same thing. V4 equals I2R4, and V4 equals, we're going to pull through here, 8 again. And we're going to have I2 as I2 here again. And we're going to have 4 again. So if we solve this out, again, I2 equals 4. Equals 2, excuse me, I'm not thinking right. And then we're going to be able to plug this into here. So 10 amps minus I2 equals 8, right? 10 amps minus 2 amps equals I1. And that equals 8 equals I1. And so that's actually the answer that we're looking for here. And that's the correct answer to the problem, not the 12. So this just gives you the wrong 2. So you're adding 2 instead of where you should be subtracting 2. And that's all because of this negative and positive here. Kirchhoff's current law, again, that's how we solve this. We use the properties of coming into a node equals coming out of a node.